Okay, let's go and get started today. Today we're talking about something that's related to what we talked about before, but also something new, which is non-deterministic finite automata. But before we do that, let's do a quick review of where we kind of finish things up, and then we're going to add a little bit to that before we move on to this new topic. Okay, first off, a review of deterministic finite automata, or automatons, or DFAs. And if you remember what a DFA was, it was kind of this abstract model of a string accepting machine. In other words, you feed in a string and it either reports, yes, I accept that string, or no, I do not accept that string, I reject that string. So in other words, it's like a little robot, and it eats strings and it tells you yes, or it eats a string and it says no. And so that's the idea behind a DFA. Now, if you remember, the way the DFA was set up is it was formally defined by this quintuple, Q, sigma, delta, S, and F. Q is a set of states, has to be finite. Sigma is the alphabet, the input alphabet. It's a finite set of symbols, also has to be finite. Then we have this transition function that basically maps elements of Q cross sigma, in other words, state symbol pairs. It maps those to resulting states. So it maps a state symbol pair. Whatever state you're in, whatever symbol comes in on the input, transitions to a new state. It could stay in the same state, but that would also be a transition back to the state you're in. And then we have a single defined start state that has to be one of our states. And we have a set of final or accepting states, which have to be a subset of our set of states. Could be all of them, could be none of them, but it's still a subset of those. Okay, and if you remember how the machine works, which I think you do, that basically you start in the start state, you read a symbol off of the string, you look that up, the state that you're in, and the symbol that you got, you look that up in the transition function that makes the machine move to a new state. After all, and you repeat that process of read the next symbol, whatever state you're in, look it up in the transition function, transition state. You repeat that until you run out of characters on the string. In the string, once you run out of characters, then if you're in a final state, you report accept or yes. If you're in a non-final state, you report no. And then additionally, you always reject if you get some spurious symbol that is not part of your alphabet. And one thing to remember is that that transition function, delta, in a formal DFA has to be a total function, meaning every state has to have every symbol accounted for in that transition function. Now, you can kind of ignore some of the ones where if it just is going to reject from that point on to enter a trap, you could leave those off in the graph, but to be a formal DFA, that has to be a total function. Okay, and here's that example we had from last time as a quick review. Here's the formal definition of the DFA. Here's the graph of what that looks like to make it a little more visual, viscerally understandable to us. So if we're in Q0, we've got three states, 0, 1, and 2. In 0 on a B, we stay there. At 0 on an A, we go to 1. 1 on an A, we go to 2. 1 on a B, we stay in 1. 2 on a B, we stay there. 2 on an A, we go back to there. Now notice that's a total function. And notice we have a single defined start state. We have a set of final states, which only has one state in this example. But there is our example drawn out in graph form to make it easier for us to look at. Now, the extended transition function of a DFA, we talked about this before, but I'm going to spend a little more time on it. Remember, the transition function is part of the definition of the DFA. In other words, if we go back here, here's the transition function. But now we've also defined this idea of an extended transition function, which basically maps, rather than Q cross sigma, it maps Q cross sigma star. In other words, this could be lambda, which would be just the same state you're in. It could be elements of that. It could be that squared, that to the third. In other words, this is mapping the state you're in with a string and then reporting what the output of that, what state that outputs when it processes that string. So in other words, a way to think of the extended transition function, it says, okay, starting in some state Q to the n, could be 1, could be 0, could be 5, whatever. We're in some state, and we feed in a string. What state does that result in? So in other words, we apply the transition function 0 or more times to exhaust the symbols in the string, and then we report what state we were in when we did that. So this is basically just saying the extended transition function, we repeatedly apply the transition function like we did back here in the rules of the thing until we don't have any more symbols in that string. And the result of that extended transition function is what state were we in when that, what state resulted from processing this string by starting in that state. All right, so a couple examples of the extended transition function in action. Here's our example. Here's what the transition function looked like. The way that defines this over here. And then we say, what are some elements of the extended transition function? Well, if we're in Q0, and that has an extra 0 in it. Let me fix that real quick so I don't forget before I publish the slides. Take that out. Okay. Okay, so if we're in Q0 and we have an AB, where do we end up? Well, let's figure it out. So we're in Q0 right here. We have A and then B. We're in Q2, so Q2 results. If I'm in Q0 and I have AAAB, so A, B, also results in Q2. If I'm in Q0 and I have BBAA, so Q0, B, A, then I'm in Q1. So notice that for every extended transition function, given some state we're in, and given some string of 0 or more symbols in our alphabet, we can always determine a single state that winds up in. It's always going to end up in one state. So notice if I'm in Q0 and I get a lambda, I'd still be in Q0. I haven't used any symbols. Q0 and a B, I get Q0. Q0 and an A, I get Q1. But Q0 and a BA, I still get Q1. All right, so that's the concept of the extended transition function for a DFA. And one thing about those quickly is notice that the number of elements in the transition function, in other words, the length of the transition function for a DFA is the number of states multiplied by the number of symbols in our alphabet. And that's always going to be finite because the number of states is always finite and the number of symbols is always in the alphabet. The input alphabet is always finite. So this is always going to be a finite number. It could be very large, but it's always going to be finite. But the extended transition function, since it's crossing the states with a set of strings, it's alphabet star, this is always going to be infinite because there's an infinite number of possible strings. Remember, the star means 0 or more symbols from this alphabet. Could be any number of them. So the length of the extended transition function is always going to be infinite. And we're going to use that extended transition function here to formally define the language that's defined by a DFA. So let's go ahead and take a look at that really quickly here. All right, so informally, we talked about this last time, but we'll review this again. Informally, the set of strings accepted by the DFA is the language defined by that DFA. Now, a more formal way to look at that is like we have down here. And I see I have another thing I need to fix here that has a font problem. Oops. Okay, so the set of all strings accepted by the DFA is the informal definition. The formal definition is if we have some DFA M, which there's its quintuple, then the language that's defined by that is the set of all strings in the alphabet star that are accepted. So in other words, the language of this machine M is all strings W, element of sigma star, such that if we use the extended transition function by starting in the start state and consuming that string, we end up in a final state. Now, one cool thing about that is that also gets us a definition for the complement of that language of that machine, which is all strings W that are in alphabet star, such that when we start with the extended transition function, use the extended transition function starting with S and consuming the string, we end up in a state that is not a final state, because Q minus F, so the set difference where we take away F from Q leaves the non-final ones. So if we end up in a non-final state, that would be the complement. So in other words, if we have any DFA, we can always easily or trivially generate the complement of that language by just taking final states and making them non-final, and taking non-final states and making them final. All right, so there's a formal definition for the language defined by a DFA. Okay, so speaking of languages defined by a DFA, keep in mind that every automaton, every finite automaton accepts or defines some language. So there are an infinite number of DFAs and an infinite number, therefore an infinite number of definable languages. So how many languages are there that we could make a DFA for? Infinite. There's an infinite number of them. And if we consider the set of all possible DFAs, then we get this set of languages that could be defined by a DFA. So in other words, if you think about that, that's creating this like infinite size set of possible languages that we could create DFAs for. And that we can think of as a family of languages. So in other words, what are all of the possible languages I could ever imagine creating a DFA for? There's an infinite number of them, but it's definitely a set. It's a set because you can have infinite sets, and that's a family of languages. And the family of languages, the name for that, the languages that we can define by using a DFA, that's called the regular languages. And you might have wondered earlier why regular expressions were called regular expressions. And the reason for that is because they can only define regular languages. And we'll get to that later on. We haven't really discussed that any further yet. But note that the family of languages that DFAs can define is the family called the regular languages. Now, the question might come up like, are there other families of languages that are beyond DFAs? And the answer to that is yes, there are. And we're going to see some of those later on in the semester. But right now, just think of if you can make a DFA, or if you make a DFA, the language it defines has to be a regular language by definition. Or if you have a regular language, you can make a DFA for it. Okay, so the regular languages, let's say we have some language, let's say it's called L1. It's called regular if and only if there exists a DFAM such that the language of the DFAM is that language L1. So in other words, a language can only be called regular, only belong to the family of regular languages if there exists a DFA that defines that language. And conversely, if you have a DFA, it defines a regular language. The language that it defines has to be regular. And that's, again, by definition. So the definition of a regular language is one for which exists a DFA. Okay, so back to the D in DFA, determinism. What makes DFAs deterministic? Why are they deterministic? And the answer to that is pretty clear, that if you look at the way that they function, that you're always in a state, a single state, and you have a single input symbol that comes in, and that single input symbol comes in, it has to be defined in the transition function, and since it's a function, there's only one entry that is in there. You can't have multiple things in their domain. So there's one thing that leads to one other resulting state. So at every step of the way, it's going to do the same thing given the same input. It's never going to make any different, take any different action when you feed it the same input. So it's completely predictable. It'll always react the same way when you give it the same input, and you'll always end up having the same result or be produced from some given string. And that means that the DFAs never really have a choice what to do when you feed a string. So in other words, this robot, you feed it a string, and if you feed that same robot that same string, it will always take the same actions, and that makes it fully deterministic. And one of the things, though, that we might consider is like, what happens if we change the rules to give that robot a form of what I have in quotes there, free will? So it can make choices about what it does with the string. It doesn't always have to do the same thing. It could decide what to do with that string. Or it might change state for no reason at all. And that's where we get to this concept of a non-deterministic finite automata, which is what today's lecture is about. So let's look at how you define an NFA, non-deterministic finite automaton. And that is, again, it's also defined by a quintuple. Same things that are in a DFA, set of states, input alphabet, transition function, a single defined start state, and a set of final states. Those things are exactly the same. So everything is the same except for the way we construct this transition function. And the way we construct the transition function for an NFA is as follows. The transition function is we cross Q with the alphabet, but we also allow lambda. So the only difference here that we've made on this side in the domain is we've added lambda to our input alphabet. So we're allowing the empty string to cause to have things that it can cause transitions in our function. The other thing we did is we changed the range. The range of this, it's mapping Q and a symbol from the alphabet or lambda. We're mapping that pair with a resulting element from the power set of Q, which remember, this is the set of all possible subsets. So this could be single states, or it could be an empty set, or it could be any subset of the set of possible states. Now, because of that change in the transition function, that has a couple of implications. The first one is that lambda is allowed as a second argument in the domain. So in other words, when we look up that function, we're allowing lambda to be in there. We're allowing to have the elements in there. In other words, the machine can change state on nothingness, on an empty string. That doesn't mean that the string has already been exhausted. That just means it could change without consuming a symbol. Now, it's not obliged to change. It could or it could not, which is why I said back here, we're going to give this thing free will. We're giving it the choice of you can change state for no reason, or you can stay where you are. And since you could have one state that leads out to multiple other states and have lambdas on both those, you could give it a choice of either you decide to do this or you decide to do that. It's up to you to decide to do that, machine. So if this was a robot, you could give it the free will to decide to take a nap or forage for food or whatever. But again, it's not obliged to take any of those lambdas. It doesn't have to, but it can if it has a transition function entry labeled for it. The second part of this is the range being the power set of Q. That means the transition function can allow a state symbol pair that maps to a resulting set of possible states on that symbol. So in other words, you could say, I'm in state 0, and on an A, I could go to a set that includes state 1 and state 2, or let's say, or state 2. So it could decide which of those two paths to take. So I say, hey, machine, or robot, I gave you an A, and it could decide to do, oh, I got an A, I'm going to take a nap. Or I got an A, I'm going to forage. So we're giving it choice on what to do when it gets that symbol A by giving it a set of possible outcomes that could happen from that. And then the third thing here is the transition function doesn't have to be a total function. And that transition function not needing to be a total function is actually a really useful thing, because now we can have this NFA that we construct where there are some things that are defined and some things aren't. But the rule still applies. If we're in a state that does not have a defined transition for that state, it immediately rejects. Okay, so those are the three main things. Notice we didn't change much of this. We just changed the transition function and how it was created, and we allowed two differences, a lambda in the domain and these subsets in the range. So in other words, a DFA is actually kind of a subset of NFAs, because you could make a DFA with this by only allowing things in the range that have single states, and over here only having transition function elements that don't include lambda. So every DFA is also an NFA, but every NFA is not necessarily a DFA. Some of them might be, but some of them might not be. Okay, so that effectively means that an NFA is like a DFA, but has transitions that can happen on lambda. And when you're in some state, you can have multiply defined edges leaving that state going to other states that have the same label on them, the same input symbol on them. So that makes an NFA non-deterministic. They have a choice whether to take the lambda transitions or not, or which lambda transition to take if there's more than one. And if there's more than one edge leaving a state labeled with the same input symbol, they have a choice as to which one of those to take. So when we give them input, they can make different choices given the same input. they could choose on an A this time I'm going to take this lambda and then the A. On this other time I'm going to go this other route and take a different lambda and then use the A. We're giving them, in a sense, this free will. All right. So let's take a look at an example. And I'm going to pause here for a second because I have a cat scratching at the door for some reason. Hold on one second. Okay. Pretty soon the cat will probably scratch at the door to go the other way. But let's go ahead and finish this example here. So here's the example for the NFA. Notice that, again, I left off the formal definition of this. I only have the graph drawn, but you can deduce all of the stuff from this. Let me turn off the notifications on that so I don't have to hear that anymore. Okay, so notice in this NFA here, there's a couple things that make this not a DFA. So let's take a look at this. So this clearly is not a DFA. The first one is notice Q0 has these weird edges leaving it with lambdas labeled on them. Can you see that? Hold on a second. Okay, there we are. So notice we have this lambda and a lambda. So notice we have lambdas leaving Q0. And also notice there's something else. We have both A's and B's in our input alphabet, but notice Q0 does not have an A transition labeled. So this is clearly not a total function, but that's okay in an NFA, not okay in a DFA. And you'll also notice over here with Q2, we have this B feeding back to itself. That is not, doesn't have an A leaving that. There's no B leaving Q1. There's no A leaving Q3. There's no B leaving Q4. And notice that Q1 has two things labeled A. There's one that stays there and then one that moves on. And same thing down here, Q3 with a B. Does it stay there or does it move on? We're giving it the choice. So this is clearly not a DFA, even though it kind of looks like one. It's got states, it's got transition functions labeled as edges, each with just a single symbol on them. It has a set of final states. Q2 and Q4 has a singly defined start state. So it looks kind of like a DFA, but it has the transitions. The way that those errors are created is different. Okay, now moving on here just temporarily, the extended transition function of an NFA. And we talked earlier, we reviewed kind of the extended transition function of a DFA, but the extended transition function of an NFA needs to be a little bit different. So the transition function itself, remember, mapped a state and a symbol, or lambda, to a resulting subset of possible states that it could go to. The extended transition function does the same thing it does for an NFA that it does with a DFA. The only difference here, again, is we're passing in a state and a string of 0 or more symbols from this. And we're mapping that to a set of possible states that could result. So in other words, if we're given a state and a string of characters from our alphabet, or lambda, then the extended transition function of an NFA results in the set of states that could result when that string is consumed. In other words, what are all of the places we could be after we consume this string? So we're not concerned about just one state we could get to. We're concerned with what is the set of all of the things that it could have done with that. So even though we're giving it free will, what we care about with this extended transition function isn't what it could have done with one path. We're saying what are all of the things it could have done when it processed that string. Okay, so that leads us to the formal definition of the language defined by some NFAM. So the language of some NFAM is the set of all strings over alphabet star, which notice, remember, star is going to include lambda, so alphabet star, such that when we apply the extended transition function actually, that should be S. Stupid font on the thing changes. Okay, we'll just pick that one. Well, let's pick the right font here. All right, good enough. So we apply the extended transition function. We start with start state S and a consume string W. If we take the intersection of that and F, it's not 0, or not the empty set. So in other words, we're saying there exists in this set that this creates some state in the set that was produced that was a final state. So in other words, that string is considered in the language if there exists some state we could get to by processing that string that was a final state. So in words, all strings W where the string can result, when processed, can result in some final state. Okay, so let's look at our example again and then try some strings using that extended transition function and then decide whether they're accepted or rejected. All right, so here, I maybe should have divided this up on separate slides, but just focus on this top one first, this one right here. So this one right here, we're saying we're feeding in the string lambda. So that's our string is lambda. So if we start with Q0, where can I get on lambda? Now remember in a DFA, if we fed in lambda, we just stayed wherever we were. We just stayed in Q0. But this is a little bit different. And the reason it's different is notice that if I'm in Q0 over here, I have some lambda transitions labeled. So without giving it any input at all, it could just slide through to there and to there, or it could have stayed here. It could have chosen not to. So the result of feeding this robot nothing is it could be in any one of three possible states. It could have stayed in 0. It could have slid through the lambda to 1. Or it could have slid through the lambda to Q3. So it could be in any one of these states. But none of those are final, so it would reject lambda. So in other words, if it had slid through to one that happened to be final, it would accept that because there is a possible way to do that. All right, let's look at one that it accepts. So Q0 on a B. So here's Q0 on a B. Well, a naive approach would be like you look at this and say, well, on a B it just stays in 0. But notice it could have slid through the lambda first, even without feeding it a lambda, because lambda is just, again, no reason. So it just slid through that without consuming any input. And then it used a B. And in here, that B could have been used there, or the B could have gone to Q4, or we could have stayed in Q0 and used the B and gotten to 0. And we also, after we used that B and got to 0, we could slide through to 1. So this is 0. It could be in any one of these states, 0, 1, 3, or 4. But this string is accepted because Q4, which I've put in boldface here, is a final state. So they don't all have to be final states, just one of them has to be a final state. So in other words, could I get to an accepting state on a B? Yes, lambda, B, accept. But I could have also gone B through to 1, or B to stay in 0, or B and slide through to 3, or slide through to 3 and then use a B and stay in 3. I could have done any of those other paths, those walks through this thing. But because there exists some one of these walks, lambda B, that matches my string, that got me to a final state, I accept. All right, let's look at another one. Let's look at Q0 on an A. So on an A, so there's no A's here, but I could have done lambda and then A, and I could be in Q1, or I could have done lambda and A and gotten to Q2. So I could be in 1 or 2, and since 2 is final, I accept. All right, BBA, let's look at that one. So BBA, so after the first B, we know we could have been in 0, 1, 3, and 4. So 0, 1, 3, and 4. And on another B, we would be in 0, 1, 3, and 4 again. And then, or no, wait, it's B, A, B. So B would get us to those, and then A from there. What are all the places I could get to with an A from there? Well, from 0, 1, 3, 4 on an A, well, I could be in 1. I could be in 2. I could be in 4. So 1, 2, and 4. But from 1, 2, and 4, I now have another B that I have to process. So 1, 2, and 4 on a B. What are all the places I can get to from those on a B? Only Q2, because there's nothing here labeled B. There's nothing here labeled B. But Q2 has one labeled B. And that one goes back to Q2. So just Q2, but since it's final, we accept. Now, Q0 BAA. So B, we know, gets us to 0, 1, 3, and 4. And now we have an A, which an A on that gets us to 4, 1, and 2. And then another A keeps us in 4 or in 1 or in 2. So it's going to be 1, 2, 4. 2 of those are final. But since all that matters is that 1 is final, we accept. Now BA, BA. So B gets us to 0, 1, 3, 4. An A gets us to, let's see, 1, 2, 4. And then a B from there gets us to just Q2. And then an A from there, so we're in just Q2 now. So just in Q2 here, in other words, there's no edge leaving this labeled with an A. So this rejects. It ends up with the empty set. There's no state I could end up here by processing BA, BA. So you could think like, well, B, A, B, but now I get another A. There's no edge labeled. Immediately reject, which ends up being the empty set. So you notice these are a little more complicated to look at because of that non-determinism, that it could really be in multiple states that it could have selected based on what path it chose or walk it chose through the graph. We gave it free will, but it still has limitations on it. It can't decide to do things that are not in the transition function. But you'll notice that it still accepts some strings and rejects some other strings. So therefore, it defines a language. All right, so the question is, like, if they're a little bit more difficult to trace through, what's the advantage of them? Why do we have NFAs? Why do we use them? And so the questions is, well, the first thing is they allow non-determinism. So for example, back here, if I fed this thing just a B, and we say, well, what state's it in? It could have chosen to be in any one of 4 states, 0, 1, 3, or 4. So what does that non-determinism give us, though? And so the initial question would be, can they represent languages that a DFA cannot represent? In other words, is there an advantage to giving this robot free will? Is there an advantage to it for what it can do if we give it free will? In other words, can they represent a broader family of languages than DFAs? Can they get us out of the regular languages? And here's a language we couldn't make a DFA for, but we can make an NFA for it because we're giving it free will. And I'm going to let you think about that here for just a second. Like, and if you think about this as like a person, you might say, well, is there an advantage to a human being having free will rather than just being the victim of fate, that whatever happens is going to happen and the world's going to do what it does? You're going to act like a automaton, like a robot, and make the same decision given the same circumstances? Or can you choose, given the situation you're in, whether you do this or do that? Is there an advantage to having that? Can you do more with having free will than without it? And the initial reaction most people have, at least with respect to, does free will give you power to do things you couldn't do without it? And the surprising answer, at least with if you tie in that free will concept with finite automata, is the answer is, maybe surprisingly, no. It does not give you any additional power to do things you couldn't do with a DFA. So in other words, if you have free will or you don't have free will, it doesn't really give you the ability to do anything that a robot couldn't be made to do, where it was a victim of fate. And I'm going to repeat that again, because somebody is going to, on the midterm or the final, answer this wrong. Every year I've made this prediction. We'll talk about this over and over again in this class, but NFAs can only represent regular languages, and for every NFA there exists a DFA that defines the same language. They have no additional power just because they allow that non-determinism. And if you don't believe me, we're going to prove that that's the case in a little bit later in the semester. We're going to prove that there is no difference between those two. Okay, so why NFAs then? So we're back to that question. If they don't give us any additional power, then what's the point of them? And the answer to that is that NFAs can be more expressive. In other words, sometimes it's easier to make an NFA that's more natural, that's a little bit easier to understand, that maybe uses fewer states, it's more compact, much more simple. And the other part of this is that it's easier to convert a regular expression to an NFA in some cases than it is to convert a regular expression to a DFA. And we're going to see that next class. Next class, we're going to look at a process for converting any regular expression you could write into an NFA. And then we're also going to continue on with proving the equivalence of NFAs and DFAs. We're going to prove that that's the case, and that's going to lead us to an algorithm that's going to allow us to convert any NFA into an equivalent DFA. In other words, given any NFA, we can make a DFA that defines the same language, and there's an algorithmic process to do that. There's a way to do that. It's kind of this mechanical process where you don't have to think about it and try to figure it out and reason, okay, well, how am I going to make this machine work? You can just basically feed an NFA into this algorithm, and it'll go and out pops a DFA. And since we can convert regular expressions to NFAs in a similar algorithmic process, that means we would have a way to convert a regular expression to an NFA, convert the NFA to a DFA, and that means that we could make a program, if we wanted, that we feed in a regular expression, and it creates this machine for us that acts as an acceptor for that string. And that stuff's going to come up again when you take the compiler design class, that this stuff, one of the heavy uses of automata in formal languages is in creating a compiler. So, for example, DFAs can be used for the tokenizer of a compiler. And remember, DFAs are super efficient because their operation is always linear. You feed it a symbol, it processes that, goes to another state, uses the next symbol, goes to another state. So in other words, it just linearly will buzz through a string, and when it gets to the end, it knows, yes, that's in this language, or no, it's not. And that's essentially what one of the first stages of the compiler is. It buzzes through the input and tokenizes that into these symbols are grouped together to make an identifier, these are grouped together to make this other if statement, these are grouped together to make a while statement, these are grouped together to be a hexadecimal constant, 0xFE, whatever. And so being able to tokenize all of that input in a linear way with a process where we could start out with regular expressions and then get a program out of it, or a machine that does that, that's one of the powerful things about them, is DFAs, super efficient. Okay, so that's all for today. Finish your DFA assignment because we're going to have some more assignments with NFAs and converting NFAs to DFAs and regular expressions to NFAs coming up. So I want you to focus on getting those DFAs done so we can go over those. And then we'll have another assignment coming up. But next class, we're going to look at kind of the equivalence of regular expressions, NFAs, DFAs, and how to convert between those things. And then eventually what we're going to do is we're going to look at going the other way with, okay, I have a DFA, how do I make that into a regular expression? All right, so that's it for today. Hopefully I didn't talk too quickly, but we're going to come back and do some more examples of these things later on. So look for that next class. All right, stay safe, wash your hands, stay out of trouble, finish your assignment. That's it.